If you stand in the middle of Kansas today, in the flat quiet of a wheat field that reaches to every horizon, you are standing on a sea floor. Not a coastline, not a riverbed, an open, deep ocean floor. 90 million years ago, the water above this spot was 600 feet deep, warm enough to swim in, and full of creatures that do not exist anywhere on Earth anymore. Lizards the size of buses hunted along its surface. Sharks the length of modern boats cruised its midwater. Turtles as wide across as a small car drifted through its currents. Winged reptiles with 6-meter wingspans glided on updrafts off its coast. The seafloor was carpeted with clams nearly 2 meters across, the largest bivalves the world has ever made. The sea they lived in was called, by the people who first began to map its deposits, the Western Interior Seaway. And for roughly 30 million years, during the long middle of the Cretaceous, it ran from the Arctic Ocean to the Gulf of Mexico, cutting North America in half. This is its story, not as a theory, not as a scattering of fossils in a museum case, but as a place, a real body of water, with a name, with a coastline, with currents and seasons, with specific creatures who were born and grew and died and fell to its floor, layer after layer, for longer than anything we would ever call history has run. A place that quietly no longer exists, and whose seafloor is now your Midwest. To understand the Western Interior Seaway, you first have to imagine North America the way it was not. 100 million years ago, the continent did not have the shape you know. It was not one unbroken landmass stretching from coast to coast. There was a narrow, north-south mountainous landmass running down the western side of the continent, from Alaska through what is now British Columbia, down through the Rockies of Montana and Wyoming, through Utah, Colorado, New Mexico, into what is now Mexico. Geologists have given this strip a name. They call it Laramidia. It was long, it was narrow in places, and it was dominated by a rising mountain belt on its western flank, formed by slow tectonic compression as the oceanic plate to the west ground under the continent. On the eastern side of the continent, there was another, larger landmass, older, lower, less tectonically active. It stretched from eastern Canada down through what is now New England and the American Southeast. Its ancient Appalachian mountains had already been through several cycles of uplift and erosion. They were still there, but much lower than they had been. This landmass is, appropriately, called Appalachia. Between these two landmasses, across what is now the Great Plains, across what is now the entire span from Texas up through the Dakotas and into Manitoba and Saskatchewan and beyond, there was water. Deep, warm, open water. An arm of the ocean that connected at its northern end to the cold Arctic seas and at its southern end to the warmer waters of what would become the Gulf of Mexico. At its maximum extent, somewhere around 90 to 80 million years ago, the Western Interior Seaway was approximately 3,200 kilometers long and roughly 1,000 kilometers wide. It was, in other words, as long as from modern Alaska to modern Mexico, and as wide as the distance from Chicago to Denver. Its deepest parts approached, in some estimates, nearly 1 kilometer in depth. In every oceanographic sense, a proper deep water body with open ocean stratification, temperature gradients, its own currents, its own ecology. This was not a lake. It was not a flooded plain. It was the ocean. It just happened to be an ocean that was also, by modern eyes, sitting inside the middle of a continent. If you had been alive in the late Cretaceous and you had wanted to cross from what is now New York to what is now Los Angeles, you could not have walked. You could not have ridden anything. You would have had to sail across open water with no land in sight for weeks of rowing, past shorelines that belonged to two entirely different landmasses. You would have passed, without knowing it, over the locations of future cities, over what would become Omaha and Wichita and Denver. You would have been at sea for the entire crossing of the interior of the continent you now live on. Let that sit for a moment. North America, as you picture it, is a relatively recent arrangement. For a significant fraction of the last 100 million years, it has not been a single piece of land. The configuration you grew up with, the continuous landmass from Atlantic to Pacific, is, geologically, a recent shape. The continent spent much of the late Cretaceous as two narrow lands with an ocean between them. How does an ocean end up in the middle of a continent? The answer is two things working at the same time: a worldwide rise in sea level and a local, slow, persistent sinking of the land. The mid-Cretaceous was one of the warmest intervals in Earth's entire recent history. Global temperatures, averaged across the planet, were many degrees higher than today. There were no polar ice caps of any significant size. Greenland was forested. Antarctica supported cool temperate plant communities. The tropics were broad, slow bands of warm water and tropical humidity. All of this had consequences for sea level. When you remove ice from the planet's surface, when you return to liquid water, all the ice that would otherwise sit on Greenland and Antarctica and the Arctic Ocean, you add that water volume to the oceans rise. In the Cretaceous, global sea level stood, by most careful estimates, somewhere between 170 and 250 meters higher than it does today. That rise alone was enough to flood vast areas of the continental interiors of every continent. Europe at the same time was mostly underwater. The great chalk cliffs of southern England, the Paris Basin, the chalk deposits of northern France are all the seafloor of this same global high sea, slowly covering low-lying Europe. South America and Africa had their own inland seas, but North America had something extra. On its western margin, a long-running tectonic event was actively depressing the crust. To the west of Laramidia, an oceanic plate, the Farallon Plate, was being subducted eastward beneath North America. Subduction zones, where one plate is being pushed under another, are among the most dynamically active features on the planet. They produce volcanoes. They lift up mountain ranges on the overriding plate. Through the weight of the thickening crust they create, produce downward flexure in the plate behind them. This is called a foreland basin. It is, essentially, a long depression running parallel to a rising mountain range, formed by the weight of the mountains pressing down on the adjacent, still elastic crust. In the Cretaceous, the Sevier orogeny, the episode of mountain building taking place along what is now the western edge of Wyoming, Utah, Nevada, and adjacent areas, was actively building a mountain range, and the foreland basin behind it, stretching out across what is now the central plains of North America, was slowly subsiding under the growing weight. By the Middle Cretaceous, this depression had sunk deep enough that, combined with the already high global sea level, it filled with water. The sea, once it started to flow in, had both a northern entrance from the Arctic Ocean and a southern entrance from the young Gulf of Mexico. It advanced from both ends simultaneously across millions of years. And when the waters from north and south met, they did so somewhere in what is now the central part of the continent. From that point on, North America was two landmasses, and the Western Interior Seaway had begun. The climate of that seaway was not like anything most of us have seen. There were no polar ice caps. There were no cold winters, in the sense that you would recognize a cold winter anywhere on the continent at sea level. The Cretaceous greenhouse was profoundly warm. Sea surface temperatures in the middle latitudes of the seaway, along what is now the central United States, likely ran between 20 and 25 degrees Celsius. The tropical end of the seaway in the Gulf region was warmer still. Even at the northern end, where the water connected to the Arctic, the conditions were cool temperate rather than Arctic. There was no permanent sea ice. The whole system was, by modern reckoning, a subtropical to warm temperate continental sea. The climate of the lands bordering it, Laramidia to the west, Appalachia to the east, was wet and warm. The western margin of the seaway in particular was lush. Behind the rising Sevier Mountains, rivers carried enormous loads of sediment eastward into the seaway, building broad deltas and muddy shelves at its western edge. Swamps of tree ferns, of cycads, of early flowering plants, of the towering gymnosperm forests that characterized the Mesozoic, lined its coasts. The coastal strip of Laramidia was, in many reconstructions, a rich biome of dinosaurs, hadrosaurs browsing in deltaic swamps, tyrannosaurs in the drier interior, ceratopsians roaming the uplands, small mammals living at their feet. On the Appalachian side, the vegetation was different, but similarly rich. The eastern coast of the Seaway bordered an older, lower, more eroded landscape, drained by sluggish rivers into sandy and muddy shelves. Its dinosaurs were less well known than those of the western side. The fossil record of Appalachian terrestrial deposits is patchier, but they were there. Hadrosaur jaw fragments have been found in New Jersey. Tyrannosaur teeth have been found in Mississippi. A whole parallel dinosaur fauna ran along the eastern shoreline of the Seaway, separated from its western relatives by open water they could not cross. This, then, is the general picture. A long, warm north-south ocean filling the middle of a continent. Two landmasses on either side, each with its own ecology, its own dinosaurs, its own climate. Broad coastal zones of swamps and forests and rivers, a deep central channel of open water. And above it all, a subtropical atmosphere, warm, often humid, storm-prone, with seasonal weather patterns that would not have felt entirely foreign to anyone who has lived on a modern coast, except that the creatures flying through the air and swimming through the water would have been unlike anything alive today. The question that follows naturally is, what lived in it? And the answer, across the 30 million years of its existence, is a very great number of things, almost none of which survived into our time. The Western Interior Seaway was one of the greatest ecosystems of the late Cretaceous. It had its own plankton communities, its own filter feeders, its own fish, its own top predators, and its own complex layered food web. When it emptied, at the end of the Cretaceous, much of that ecosystem emptied with it. What is left now are their bones and their shells scattered through the chalks and the shales of the American interior, waiting to be read. The most abundant organism in the Western Interior Seaway was almost certainly something you would never see with the naked eye. In the sunlit upper 30 or 40 meters of the Seaway, in concentrations so dense that a single liter of water would have contained many hundreds of thousands of individuals, drifted a microscopic single-celled alga called a coccolithophore. Coccolithophores are tiny photosynthetic organisms, each one roughly the size of a bacterium, armored with a covering of even smaller calcium carbonate plates called coccoliths. Each one a precisely shaped disc or shield are secreted by the cell during its life. When the cell dies, or when it is eaten by zooplankton and its plates are passed through the gut, the coccoliths shed from the living cell and sink slowly toward the sea floor. They sink at different rates depending on their size and their attachment to organic matter, but most of them, across the broad middle sections of the Seaway, reach the bottom eventually. They accumulate. They form a fine, pale mud of calcite particles, each one originally the living armor of a microscopic alga. And when that mud is buried, compressed across millions of years, it hardens into a distinctive rock. The rock is called chalk. The chalks of the Niobrara Formation, exposed today across large areas of Kansas, Nebraska, eastern Colorado, and Wyoming, are essentially compressed rain of coccolithophores. You can hold a lump of Smoky Hill chalk in your hand and know that at the scale of its component particles, it is nothing but the calcified bodies of late Cretaceous algae. Every centimeter of thickness represents thousands of years of slow plankton rain, a small fraction of a millimeter per year across the deep quiet of the Seaway bottom. If you have ever seen the White Cliffs of Dover, you have seen the same kind of rock from the same global Cretaceous high sea laid down at the same time. The chalk of the English Channel and the chalk of central Kansas are part of one ocean-spanning phenomenon, a worldwide peak in coccolithophore productivity in warm, high sea level conditions, accumulating on broad, stable shelves preserved for 100 million years. What you're seeing when you see any of these chalk exposures is the preserved surface of a deep plankton-fed sea. Kansas, at its Cretaceous maximum, was as much a chalk factory as the North Sea. And the chalk is still there. It is still, in many places, at or near the surface. Farmers cut into it, rivers expose it, wind erosion carves it. The floor of the Western Interior Seaway, in much of its former extent, is not buried under miles of later rock. It is a meter or two down. It is sometimes on top, and inside it, the larger fossils wait. Of all the creatures of the seaway, the ammonites are, in some ways, the easiest to love. They are coiled shell dwellers, distant relatives of the modern nautilus, and very close relatives of the modern squid and octopus. Inside each ammonite shell, when the animal was alive, lived a soft-bodied cephalopod with tentacles, a parrot-like beak, excellent vision, and the neural complexity we now associate with living cephalopods. Ammonites had been in the world's oceans since the early Devonian, more than 300 million years before the Western Interior Seaway formed. They had survived the End-Permian extinction. They had survived the End-Triassic extinction. They had, by the Cretaceous, reached one of the highest diversities they would ever achieve. The seas of the late Cretaceous were, in every measurable way, a golden age for them. In the Western Interior Seaway, ammonites were everywhere. Their shells are the single most common macroscopic fossil in the Pierre Shale and the Upper Niobrara. You can walk today across exposed shale outcrops in South Dakota or Wyoming and find ammonite shells within an hour, if you know what you are looking for. Most of them are small, a few centimeters across, elegant spiral forms. Plesiosaurs, one of the more common genera of the seaway, sometimes reached close to a meter in shell diameter. A less common but spectacular genus, known from equivalent European deposits, could reach over 2 meters, a creature with a living body the size of a small car. And some of the late Cretaceous ammonites did something strange with their body plan. Rather than coiling, they uncoiled. Perhaps the most abundant ammonite of the Western Interior Seaway had a shell that was essentially a straight, slightly tapered cone, sometimes over a meter long. It lived, probably, with the narrow end angled downward and the wide opening facing up, drifting vertically in the water column like a living spear. Other genera, Didymochorus, Mosasaurs, coiled their shells in bizarre helical or heteromorph forms, tight spirals wrapped around an axis like a twisted corkscrew, or shells that suddenly reversed direction partway through their growth and grew the other way. Nobody is entirely sure what these strange forms were doing ecologically. One hypothesis is that they were specialized for very low-speed hovering lifestyles in quiet water, filter feeding on zooplankton. Another is that they were making themselves harder for predators to swallow. Whatever the reason, the late Cretaceous was a period of exuberant ammonite experimentation, and the Seaway recorded more of those experiments than almost any other deposit in the world. Ammonites in the Seaway were near the bottom of the food web. They were hunted by fish, by larger mollusks, by reptiles. We know this because we find ammonite shells with characteristic bite marks pressed into them, punctures matching the teeth of mosasaurs and sharks. Sometimes the punctures are not holes but dents, the shell held under the pressure of a failed bite, kept by the animal as a healed scar and preserved. One of the most famous early pieces of evidence for mosasaur feeding behavior came from a large Plesiosaurs shell marked with a perfect arc of tooth impressions that exactly matched a known mosasaur jaw. The ammonites did not survive the end of the Cretaceous. Every one of their lineages, after more than 300 million years of persistence, ended at the same boundary that ended the non-avian dinosaurs. The Western Interior Seaway, by the time the asteroid fell, was already largely drained. But the ammonites that had thrived in it were, across the wider oceans of the late Cretaceous, still abundant, still diverse, still evolving. Their absence from every rock above the Cretaceous-Paleogene boundary is one of the sharper signals in the fossil record. The seas that came after were seas without ammonites for the first time in 350 million years. On the floor of the seaway, in places where the water was not too deep and the bottom was reasonably stable, there lived a different kind of animal, less charismatic than the ammonites, but in some ways no less remarkable. They were bivalves, clams, creatures in two-shelled hinged shells, filtering plankton from the water and growing slowly across many years. The particular family that dominated the seaway's deep-water seafloor is called the Inoceramids, or Inoceramids, and their defining feature in the context of the late Cretaceous was their size. Many Inoceramids were ordinary in size, 10 or 20 centimeters across, comparable to the larger modern clams you might encounter in a fish market, but some of them were not ordinary. The genus Plesiosaurs, which dominated the deeper, quieter parts of the Niobrara seafloor, routinely grew to a meter in diameter. The largest known specimens approach, and in exceptional cases exceed, 2 meters. That is a shell nearly the size of a bathtub, a single animal holding its massive shells open to the seawater, filter feeding for years on the rain of plankton falling past it. They were the largest bivalves the Earth has ever produced. They thrived, we think, by virtue of a very particular adaptation to life on soft, muddy bottoms. The deep floor of the Western Interior Seaway, during its peak anoxic intervals, was a difficult environment, poorly oxygenated, soft, prone to sinking. A heavy-shelled clam in this environment would have sunk into the mud and suffocated, but an Inoceramid, by growing its shell extraordinarily thin in proportion to its size, some Platyceratops shells are only a few millimeters thick despite being over a meter long, could spread its weight across a large area. It floated, in effect, on top of the mud rather than pressing into it. Large Inoceramid shells in some parts of the Niobrara and Pierre form a kind of shelf ecosystem of their own. Their inside surfaces, after their inhabitants died, provided hard substrate in what was otherwise a uniformly soft sea floor, and a whole ecology of small organisms colonized these shell interiors, using them as the only solid ground for hundreds of kilometers in any direction. Tiny attached bivalves, serpulid worm tubes, bryozoans, encrusting foraminifera all lived on the inner surfaces of Inoceramid shells. The dead clams, in effect, became the reefs of the deep seaway, and every one of those Inoceramid beds across Kansas and Nebraska and the Dakotas is exposed in many places within a short drive of a modern highway. For all the slow grandeur of the plankton, the ammonites, and the giant clams, the seaway was also an active hunting arena. And to understand how active, you have to meet one of its signature residents. Its name is Zephactinus audax. It was a fish, a bony fish, belonging to a group called the Ichthyodectiforms, distantly related to modern tarpon and herring. And it was enormous. Adult Zephactinus reached 6 meters in length, with a massive heavy-jawed head full of long, sharp, needle-like teeth, a deep muscular body, and a tail built for short bursts of explosive speed. It was, in the ecology of the seaway, one of the largest predatory bony fish of its era. A full-grown Zephactinus suddenly appearing out of the blue of the seaway water was something no smaller fish in the system would have survived. But the thing Zephactinus is most famous for is not its size. It is a single specimen. A fossil hunter working the Niobrara chalk of western Kansas found, preserved beautifully in a slab of stone, an adult Zephactinus about 4 meters long. And inside its body cavity, visible through the dissolved bones of its ribs, was another fish, almost intact, nearly 2 meters long. Another predator, a Gillicus, swallowed whole. The Xiphectinus had caught and eaten a fish nearly half its own length, probably because the prey struggling had torn something vital inside it, had died with the meal still in its gut, and sunk to the sea floor and been buried intact. The fossil is now on public display in the Sternberg Museum of Natural History in Hays, Kansas. It is sometimes called simply the fish within a fish. It is, in almost any paleontology textbook, one of the most immediate visual arguments for the ecology of the Cretaceous seas. A 6-meter predator eating a 2-meter predator caught in the last moment of its own life, preserved in chalk for 110 million years. Xiphectinus was not the only large predatory fish in the seaway. Protosphorana, a barracuda-like creature with long, sharp jaws, cruised the midwater. And Codus, the so-called saber-tooth herring, had 2 enormous fang-like teeth projecting from its palate and was common enough that its isolated fangs are a frequent casual find in Kansas. The seaway supported a complete vertical food column of bony fish, from plankton feeders at the small end to apex predators like Xiphectinus at the top. But even Xiphectinus was not, in the deepest sense, the top of the food web. Above the fish, in the upper water column, something else was cruising, something that had, relatively recently, returned to the sea from the land, something that would, in the final millions of years of the seaway, become the defining predator of the entire system. The mosasaurs were lizards. This is one of the strangest things about the late Cretaceous oceans. The top predators of the Western Interior Seaway and of almost every marine ecosystem worldwide at that time were not fish. They were not ichthyosaurs. Those had gone extinct 30 million years earlier. They were not the plesiosaurs, though plesiosaurs were still common. They were lizards. Actual lizards, close relatives of the modern monitor lizards of Southeast Asia, or the modern anguid lizards, which had, within the preceding 20 or 30 million years, returned to the sea and adapted their bodies for full-time aquatic life. The transition had been, by geological standards, quick. Earliest mosasaur ancestors appear in the Turonian and Coniacian ages of the Cretaceous, perhaps 90 million years ago. They are small, less than a meter long, still quite lizard-shaped. Within 20 million years, they have produced creatures that are the most effective oceanic predators on the planet. Tylosaurus proriger, the largest and probably most famous of the Western Interior Seaway mosasaurs, reached lengths exceeding 13 meters. Some exceptional specimens are estimated at close to 15 meters. A full-grown Tylosaurus was longer than a city bus. Its jaws carried rows of conical teeth with an additional set of secondary teeth on the palate, a feature shared with modern monitor lizards that helped grip prey and drag it down the throat. Its body was long and serpentine, with paddle-like limbs and a long, powerful tail, ending in a downturned fluke reminiscent of a shark's. They swam by undulating their long bodies in the same side-to-side motion that modern monitor lizards use on land, only now rendered smooth and continuous and driven by a strong muscular tail. They were pursuit predators, capable of sustained swimming, and they appear, from the structure of their inner ear bones, to have been quite fast. What did they eat? Almost everything else in the seaway. We have direct evidence of mosasaur feeding from stomach contents preserved in exceptional fossils. Tylosaurus specimens have been found with, inside their rib cages, the bones of smaller mosasaurs, of plesiosaurs, of fish, of seabirds. Other mosasaur genera specialize differently. Globidens, a smaller, stockier mosasaur known from the later seaway, had rounded, bulbous teeth adapted for crushing shelled prey. It almost certainly fed primarily on ammonites and on Inoceramid clams. Platecarpus was slimmer, probably faster, hunting fish and smaller cephalopods. Cladastes was a mid-sized generalist. The Seaway, by its later ages, had an entire guild of mosasaurs, each adapted to a different ecological role. Whale-sized apex predators, medium-sized fish hunters, specialist shell crushers. They had, across 20 million years, occupied roles that would today be held by a mix of killer whales, large sharks, dolphins, and walruses. A full-grown Tylosaurus was, in the Seaway's food web, what a modern adult orca is in the North Pacific. And they were, until very nearly the end, the most conspicuous creatures in the water. There is something deeply strange about this. The mosasaurs are one of the clearest cases in the fossil record of a group of terrestrial vertebrates, animals descended from ancestors that had left the sea 300 million years earlier, had spent that entire time on land, had developed lungs, had evolved all the architecture of terrestrial life, returning to the ocean, and within a geological blink, dominating it. They are, in the same sense as the whales, a reminder that the sea does not permanently select for any one body plan. Every so often, in deep time, something comes back from the land, and for a while, it wins. But the mosasaurs were not alone at the top of the Seaway food web. Another group of marine reptiles shared the upper waters with them, a much older group, one that had been in the ocean since the Triassic, and which, by the Cretaceous, had produced some of the most distinctive bodies the vertebrate record contains. These were the Plesiosaurs. If the mosasaurs were the sharks of their world, fast, long-bodied pursuit predators, the Plesiosaurs were something else entirely. They had broad, flat bodies, roughly the shape of an overturned bowl, propelled through the water by 4 long paddle-like flippers. They swam by, flapping these flippers in a motion more like flying through water than ordinary swimming, each pair of limbs sweeping through the water in coordination. And they had, projecting from the front of their bodies, the single most exaggerated neck anatomy in the history of vertebrate life. The genus Elasmosaurus, whose remains are common in the Pierre Shale of South Dakota and Kansas, reached a total length of approximately 14 meters. More than half of that was neck. An adult Elasmosaurus had 72 separate neck vertebrae, one of the highest vertebrate counts on record, far higher than the 7 that you or any other mammal possess. Its head sat at the end of this enormous serpentine neck, and its mouth was small, full of needle-like interlocking teeth. Elasmosaurus did with its neck has been a subject of debate for over a century. Early reconstruction showed it reared up like a plesiosaur cobra, striking down at fish from above. More recent biomechanical analyses suggest this was not possible. The neck was too long and too laterally restricted for dramatic S-shaped motions. The currently favored picture is different and, in a quiet way, even stranger. An Elasmosaurus, most likely, cruised slowly through schools of small fish, holding its long neck forward and below, the head perhaps only half visible through the water column ahead. The fish, seeing a small head but not the enormous body behind it, did not panic. The plesiosaur, with a small, slow motion, would strike, and before the school had time to realize anything had happened, a fish had been taken. It is a kind of hunting that relies on the disconnection between body and head. Thin neck is a mechanism for getting close without the prey noticing. It is the same logic, in a different shape, as a heron's beak. There were smaller, shorter-necked plesiosaurs in the Seaway too, the polycotylids, which looked almost like reversed mosasaurs with long, narrow jaws and short, powerful necks built for fast striking. Dolichor hinchops, one of the common genera, was about 3 meters long, streamlined, and probably fed on midwater fish in a fast pursuit mode. It coexisted with the long-necked elasmosaurs, occupying a different niche, and both groups persisted in the Seaway until nearly its end. Beneath the marine reptiles, cruising the middle water in their own mode of predation, were the sharks. And the sharks of the Western Interior Seaway included some of the most impressive members of their lineage that have ever existed. The most famous of them is Cretoxerina mantelli. It is sometimes called the Ginsu shark because the knife-sharp edges of its serrated teeth, which are common fossils in the Niobrara chalk, reminded the paleontologist who first proposed the name of the precision-edged Ginsu brand kitchen knives that were being advertised on American television at the time. The nickname stuck. Adult Cretoxorhina reached lengths of 6 to 7 meters, comparable to modern great white sharks. It was, in every mechanical sense, a great white equivalent, fast, pursuit predatory, with cutting teeth designed to remove large bites from prey. Its fossil teeth have been found embedded in the bones of plesiosaurs, of mosasaurs, and of large fish. In the ecology of the seaway, Cretoxorhina was one of the clear top predators, competing with the mosasaurs for large prey. Some fossils preserve evidence of direct encounters: Cretoxorhina teeth in mosasaur bones, mosasaur teeth in Cretoxorhina bodies. They ate each other. Which one was the overall winner of those encounters likely depended on size, circumstance, and luck. Other sharks of the seaway occupied different roles. Squalicorax, sometimes called the crow shark, was a scavenger and opportunistic predator, with serrated teeth ideal for slicing flesh. Its teeth are found on the bones of almost every kind of prey the seaway produced: on mosasaurs, on plesiosaurs, on turtles, on dinosaurs that had washed into the water from nearby coasts. Squalicorax bite marks on dinosaur bones are, in fact, some of the clearer direct evidence for how close certain terrestrial animals came to the seaway margins. A dinosaur carcass floating down a river into the coastal shelf would have been consumed by scavenging sharks within days. Tychidus, one of the more specialized seaway sharks, had thick crushing teeth arranged in pavements, and it probably fed on shelled prey, ammonites, Inoceramid clams, the bottom-dwelling invertebrates of the shelf. The largest Tychidus specimens, from teeth alone, have been estimated at up to 10 meters in length, making it one of the largest sharks that have ever existed. The estimate is controversial because we only have teeth and some vertebrae to go on, but even conservative estimates put Tychodus in the range of the largest modern sharks. The seaway, then, was not a monoculture of a few top predators. It was a layered community, with multiple apex predators dividing the prey between them. Mosasaurs taking large pursuit prey, plesiosaurs specializing in stealth, sharks in their own active hunting roles, each of them interacting with the others in ways we can only partly reconstruct from bite marks and gut contents, and the occasional exceptional fossil. Above the water, different creatures ruled. Pteranodon, one of the largest flying reptiles that has ever existed, was common along the western shores of the seaway. Adult pteranodons had wingspans of between 5 and 7 meters. Their bodies were small relative to their wings, lightly built with long, narrow, toothless beaks and distinctive rear-swept head crests that varied in size between individuals and possibly between sexes. They were not pterosaurs built for long, slow gliding, the way some of the very largest pterosaurs of the later Cretaceous were. They were, instead, something closer in style to modern albatrosses, fast soarers, efficient at using ocean updrafts, capable of traveling long distances in search of prey, diving to snatch fish from near the surface of the water. Their fossils are abundant in the Smoky Hill chalk of Kansas. Thousands of specimens have been collected. The population of pteranodons that cruised the western shore of the seaway across hundreds of thousands of years must have been enormous. Nyctosaurus, a smaller, stranger relative of Pteranodon, also inhabited the airspace above the seaway. It had a far more exaggerated head crest, in some species, a long forked projection rising from the skull in an antler-like form, whose function, like so many pterosaur crests, remains not entirely clear. There were seabirds, too, of kinds that no longer exist. Hesperornis, a large flightless diving bird, reached almost 2 meters in length and swam in the seaway's surface waters, diving for fish with a body plan that resembled a modern loon or grebe, but carried teeth, actual teeth, set in its jaws, a feature seabirds would not carry again. Ichthyornis, a smaller flying relative, was in many ways the ancestor of modern seabirds, but also carried teeth and occupied ecological niches similar to modern terns or gulls. And in the deeper water, moving between the mosasaurs and the plesiosaurs and the sharks, drifted one of the largest animals that has ever lived in the sea. It was a turtle, Archelanus chiros. An adult archelan measured flippertip to flippertip across its broad, flat body, spanned approximately 4.5 meters. Its weight, estimated from skeletal measurements, approached 2 tons. It was, by every measurement we have, the largest sea turtle in the Earth's entire history. It did not have a solid shell the way modern sea turtles do. Instead, its carapace was made of a frame of supporting bones overlain by a leathery skin, similar in structure to the modern leatherback. It fed probably on soft-bodied prey in the midwater, large jellyfish, cephalopods, soft cnidarians. Its powerful jaws could close on almost any prey up to about its own head size. A full-grown archelan, drifting slowly through the warm green waters of the seaway, was bigger than most modern cars. It was, in its own strange way, one of the most peaceful creatures in the ecosystem. A slow, gentle giant in a water column otherwise dominated by active predators. Of all the creatures of the Western Interior Seaway, the ones that most surprise a modern ear are the birds. Birds in the late Cretaceous were already a well-established group. The first ancestral birds had diverged from their theropod dinosaur relatives in the late Jurassic, more than 60 million years before the Seaway formed. By the Cenomanian and Turonian, birds were diverse, globally distributed, and already occupying a wide range of ecological roles. But they were not yet the birds we know. Modern birds, crown group aves, the group that includes everything from ostriches to hummingbirds, did not yet dominate. The late Cretaceous avian fauna was full of other lineages, most of them experimental, most of them now gone. And 2 of those lineages in the Seaway left extraordinary records. The first is Hesperornis. Hesperornis regalis was a large, flightless diving seabird. Its adult body length reached between 1.5 and 2 meters, making it one of the largest diving birds ever to exist. It was built, in every measurable way, for life in the water. Its wings were tiny, vestigial stubs incapable of flight, probably incapable of any meaningful propulsion even underwater. Its legs, in contrast, were massively developed, powerful, set far back on the body, with flat, broad feet that probably carried webbing for paddling. It swam, from all indications, the way modern loons and grebes swim, by kicking with its hind legs, with its body held in a streamlined posture, its neck reaching forward to strike fish as they were sighted. And Hesperornis had teeth. Its long, narrow beak was lined along the sides with small, sharp, curved teeth, real teeth, set in sockets anchored into the jaw. The pattern of tooth implantation is unmistakably bird-like in its finer detail, but the teeth themselves are a direct inheritance from the non-avian theropod dinosaur ancestors of birds. Modern birds, for reasons still debated, lost their teeth across the latest Cretaceous and Paleogene. But Hesperornis, at the end of the Cretaceous, still had them. They would have been useful. A 2-meter diving bird with a long, snake-like neck and a mouthful of recurved teeth, hunting small fish in a crowded seaway. The teeth prevented prey from slipping out once caught. Hesperornis specimens are abundant in the Smoky Hill chalk. Some are preserved with stomach contents, confirming a diet of small fish. They must have been, across the seaway's later ages, a common sight along shorelines and across shallow shelves. Slow, graceful, strange creatures, all but impossible to confuse with anything in a modern ocean. And then, at the Cretaceous-Paleogene boundary, they were gone. Every species, every individual, the entire lineage. The other great seaway bird is Ichthyornis. Ichthyornis dispar was smaller, lighter, and unlike Hesperornis, capable of flight. Its adult body length was perhaps a half meter, with a wingspan roughly a meter. It occupied, ecologically, roles similar to modern terns or gulls, flying above the seaway's surface, spotting fish, diving briefly to catch them, returning to the air. Its skeleton is elegant and bird-like in almost every detail. If you saw its reconstructed silhouette against the sky, you would probably just call it a seabird. But its mouth, like Hesperornis, was full of teeth. The combination of very modern-looking flight-capable bird bodies with tooth-filled jaws is, in the fossil record, one of the clearest signatures of late Cretaceous bird evolution. Ichthyornis, in particular, occupies a key position near the origin of crown group birds, very close to the lineage that will produce all modern birds, but still carrying the dental inheritance that will disappear in the survivors of the KPG. Between Hesperornis in the water and Ichthyornis in the air, the Western Interior Seaway had a bird fauna that was, to any modern eye, both very familiar and deeply strange. Familiar in body plans, in ecological roles, in general silhouette. Strange in the teeth, in the particular shapes of the skulls, in the fact that the diving bird was as large as a small child and could not fly at all, and that even the tern-like flyers carried mouths full of sharp enamel. They, too, are gone. The exposed chalks of Kansas preserve their bones by the thousand, their songs, their calls, the shape of their flight on the open wind of the seaway afternoon. All of that is irrecoverable. Only the bones are left. It is worth pausing here to try to imagine what all of this was like at the height of the seaway's existence. Picture, for a moment, standing on the western shoreline of the seaway, somewhere in what is now eastern Wyoming, in the late Santonian age, perhaps 85 million years ago. The day is warm. There is no winter and no real summer, only the long subtropical steadiness of a Cretaceous year. Behind you westward, the land rises gradually toward the forested lower slopes of the Sevilla mountain belt, still active volcanoes smoking distantly along the crest. Between you and those mountains are kilometers of river-fed delta plains, swamps of tree ferns and scythes, flatlands populated by hadrosaurs and great migrating herds, by small, furtive, rat-sized mammals in the undergrowth, by the ancestors of the Tyrannosaurs that would dominate the continent 20 million years later. In front of you, eastward, the sea begins. The shoreline is broad and quiet, muddy and gently sloping, with brackish lagoons and tidal flats extending far out into the water. Beyond the shelf, the water deepens steadily, the bottom dropping away into the dim green middle water of the seaway. The surface is calm today. Light ripples move across it. The far horizon is, as it always is, nothing but water and sky. Appalachia, the eastern landmass, is 1,000 kilometers away. You cannot see it. You cannot imagine it. For the purpose of daily life, the seaway is infinite. In the water, the ecosystem runs. Coccolithophores, invisible to you, fill the sunlit upper water with photosynthesis, each tiny cell making its small contribution to the vast plankton rain. Zooplankton graze on them. Juvenile fish hunt the zooplankton. Baculites drift vertically, their straight shells pointing downward, sampling the water column. Pteranodons, 20 meters above your head, circle on thermals, their long wings barely moving, their heads turned down toward the water for the glint of a fish near the surface. A pod of small mosasaurs, perhaps 3 or 4 meters long, ripples past the shelf edge, visible for a moment as a set of dark torpedo-like shapes pushing bow waves ahead of them. Further out, the water is too deep to see anything from shore. A hadrosaur, drinking at the river mouth to your left, splashes a footful of water into the shallows. A carnivorous theropod hidden in the trees behind you has seen it. The ecology of land and sea interlocks here in constant traffic at this slow boundary where two worlds meet. If you turn your head, you can hear the surf, soft and regular. You can hear faintly the calls of Ichthyornis over the shelf, thin and sharp like the modern cries of terns. You can smell the mixed air of salt and swamp, of damp vegetation and ocean, of a living planet in its Cretaceous fullness. This went on for 30 million years. Not as a single unchanging day, of course. The sea had storms and seasons and deeper shifts. Ocean anoxic events, during which large parts of the deeper water became oxygen poor, happened in pulses. Population cycles of the dominant plankton rose and fell. New mosasaur species appeared, old ones went extinct. Climate drifted. The shoreline advanced and retreated with global sea level. But the underlying system, a warm, shallow continental sea with its own ecology, splitting North America in half, persisted with enormous stability through the entire long middle of the late Cretaceous. For longer than humans have had any settled civilization, multiplied many hundreds of times over, the normal condition of the continent. Let the day, where you are standing on that Cretaceous shoreline, draw slowly toward evening. The light softens. The Pteranodons, returning from their long afternoons soaring out over the deeper water, come in low over the beach, their shadows crossing the sand in silent, swift passes. Their cries, thin and high, echo back from the dunes behind you. The tide, if there is one in this enclosed sea, and there is some, though weaker than in a fully open ocean, begins its slow inward turn. The small shore crabs, ancestors of lineages that will not diversify properly for another 20 million years, scuttle through the lagoon shallows. Somewhere out past the shelf break, a feeding frenzy of small mosasaurs briefly ripples the surface, the blue-gray backs of 3 or 4 animals breaking the water simultaneously as they push a school of fish against itself. It sets, as it always has, over the western mountains, behind the rising volcanoes of the Sevier Arc. The colors along the horizon, in this warmer, moister, more humid atmosphere, are often more saturated than anything a modern high-latitude observer would see. Long, slow gradients of coral pink, of burnt orange, of a particularly rich violet at the upper edge. The sea, for a few minutes after the sun is gone, holds the color of the sky in its flat, quiet surface. And then the night comes. The night of the Cretaceous above the seaway is dark in a way that no modern sky is. There are no human lights anywhere on the continent. There are no lights of any kind on Appalachia far to the east, or on Laramidia behind you, or on any of the islands that dot the seaway's shallow parts. The stars are visible from horizon to horizon, undimmed in constellations that are partly recognizable. The major bright stars have changed position relatively little in the last 100 million years, though some have moved significantly. And the Milky Way, stretching across the sky, is as clear as it is on the remotest modern beach. The moon, a little closer to Earth than it is today, is very slightly larger and moves slightly faster. Its light, falling on the seaway's surface, turns the whole water to a sheet of slow silver. The night creatures take over. Deep-water mosasaurs, perhaps larger on average than the daytime ones, rise toward the shallower water to hunt in the dimmer light. Nyctosaurus, the strange antler-crested pterosaur, may hunt over the surface at night. We do not know for certain, but its large eyes suggest the possibility. Certain squid relatives, toothids, coleoids, close relatives of modern squid, rise from the deeper water to feed in the upper 100 meters of the column, as their modern descendants still do, and certain fish follow them to feed on them in turn. The sea is quieter at night, but it is not asleep. It is only differently active. You, standing on the shoreline in the warm dark, could listen to the sound of the surf and the distant calls of seabirds and the soft tick and rustle of the vegetation behind you, and you could feel yourself inside an ecosystem as complete and as breathing as anything modern. The Cretaceous night on the shore of the Western Interior Seaway was, in almost every way, alive. And then, slowly, it began to end. What ended the Western Interior Seaway was not a meteor, not a single disaster, not a change in climate. It was tectonics. In the late Cretaceous, the long-running Sevier orogeny was joined, across what is now the western United States, by a new phase of mountain building. It is called the Laramide orogeny, and it differs from the older Sevier in the style of its deformation. Where the Sevier had produced a conventional fold and thrust mountain belt along a narrow line near what is now the Utah-Nevada border, the Laramide produced much more distributed uplift far inland. The basement rocks of what would become the Central Rocky Mountains, the big block-shaped ranges of Colorado, Wyoming, and Montana, were being pushed up by deep crustal processes thought to relate to an unusually shallow angle of subduction of the Farallon Plate beneath North America. As those interior ranges rose, the foreland basin that had previously subsided under the weight of the Sevier Mountains, the basin the Seaway had filled, began to change shape. Parts of it were broken up by rising blocks, parts were tilted. The slow, steady downward flex of the crust, which had been depressing the continental interior for tens of millions of years, gradually gave way to a more complex pattern of localized uplift in intervening basins. At the same time, global sea levels, which had been at their Cretaceous maximum during the mid-part of the period, began to fall. The greenhouse climate was slowly cooling. Small amounts of polar ice may have begun to accumulate by the late Campanian. Whatever the reasons, the sea level that had supported the Seaway at its great inland extent was no longer available at the same amplitude. The Seaway, across millions of years, began to contract. It withdrew from the western coast first, as the Laramide uplifts pushed the shoreline eastward. It withdrew from the southern and northern entrances more slowly, but steadily. The deep center of the Seaway persisted longer than the shallow margins. By the Maastrichtian Age, the last age of the Cretaceous, the Western Interior Seaway was a much narrower strip, a long, thin arm of the ocean running down the middle of the continent, still connecting north to south, but no longer the vast inland sea of earlier ages. By the very end of the Cretaceous, around 66 million years ago, the connection between the Seaway and the Gulf of Mexico had closed. The northern arm had narrowed. What had been a 3,000-kilometer-long ocean was, in its final millions of years, a shrinking relic. The last deep-water parts of it, in what is now North Dakota and Saskatchewan, were drained by the early Paleocene. The continent, for the first time in 30 million years, was one unbroken landmass from coast to coast. And into this slowly draining sea, at the very end of its existence, came the KPG extinction event. The asteroid that ended the Cretaceous, the approximately 10-kilometer object whose impact crater, the Chicxulub structure, sits off the coast of the Yucatan Peninsula, struck roughly 66 million years ago. The Seaway, by this point, was already largely gone, but its last creatures, the last mosasaurs, the last ammonites in the residual basins, the Plesiosaurs, were exposed to the same global catastrophe that ended the non-avian dinosaurs. They did not survive. Every one of the mosasaurs, all of the species that had dominated the Seaway for 20 million years, is extinct by the base of the Paleocene. Every one of the Plesiosaurs, after more than 130 million years of existence, ends at the same boundary. Every ammonite species that the Seaway had produced, every ammonite species worldwide ends at the boundary. Cretoxerina is gone, Squalicerax is gone, Zephactinus is gone, Archelon is gone, Pteranodon is gone. The entire fauna of the Western Interior Seaway, everything distinctive about it, ends at or shortly before the end of the Cretaceous. The sea had already been draining for 10 million years. The asteroid finished its survivors. It is worth walking through the mechanics of that draining slightly more slowly, because it is one of the most interesting tectonic puzzles in the geology of North America. The Laramide orogeny is, in every way that matters, unusual. Most major mountain building events on the overriding plate of a subduction zone, The Andes today, for example, produce a narrow belt of mountains and volcanoes relatively close to the coast. The Sevier orogeny in the earlier Cretaceous had behaved exactly like that. A fold and thrust belt running along what is now the Utah-Nevada border, relatively close to the Pacific margin, with the Foreland Basin extending eastward behind it. Beginning in the latest Cretaceous and continuing through the early Paleogene, did something different. It produced uplift hundreds of kilometers inland. The Rocky Mountains, as we know them, the big basement chord ranges of Colorado, Wyoming, and Montana were pushed up far from any coast by deep crustal processes acting beneath the continental interior. The most widely accepted explanation is that the Farallon Plate, subducting beneath North America, did so at an unusually shallow angle during this interval. Instead of plunging steeply into the mantle shortly after the plate boundary, it slid nearly flat beneath the continental lithosphere, penetrating inland for hundreds or thousands of kilometers before descending. The friction and the coupling of this shallow slab with the overriding crust transmitted compressional stresses far inland. And those stresses slowly broke and uplifted the interior of the continent, producing the Laramide Ranges and, incidentally, breaking up the foreland basin that had held the seaway. As the basin fragmented, different segments of the seaway responded differently. The southern end, connected to the Gulf of Mexico, closed first, perhaps 75 million years ago. The last seaway waters in what is now Texas and Oklahoma retreated southward and connected, eventually, only to the open Gulf. The deep center of the seaway, in what is now the Dakotas and eastern Wyoming, persisted longer. The northern connection to the Arctic narrowed more slowly, becoming a long, thin strait through Alberta and the Northwest Territories. By the latest Cretaceous, the remaining water was a series of disconnected or barely connected shallow basins, no longer a unified ocean. And on the shrinking western coastlines, in the final ages of the seaway, some of the most famous dinosaur ecosystems in the world were taking shape. The Kaiparowits Formation of southern Utah, the Two Medicine Formation of Montana, the Dinosaur Park Formation of Alberta, and others. All of these preserved terrestrial faunas from what was, at the time, the coastal strip of Laramidia bordering the last seaway. Hadrosaurs in enormous herds, ceratopsians with extraordinary horns and frills, ankylosaurs heavily armored against tyrannosaur attack, and the earliest members of the great tyrannosaurids themselves, predecessors of Tyrannosaurus rex, hunting along the coastal plains. These were animals that lived, in effect, on the last beaches of the Western Interior Seaway. By the very end of the Maastrichtian, roughly 66.5 million years ago, the last remnants of the seaway were fading. The Hell Creek Formation and the Lance Formation of Montana, Wyoming, and the Dakotas, the famous deposits that preserved Tyrannosaurus rex, Triceratops, Edmontosaurus, Ankylosaurus, and the other iconic latest Cretaceous dinosaurs, were accumulating on what had, only a few million years earlier, been shallow marine shelves. The coast was retreating. The continent was reassembling itself, for the first time in 30 million years, into one unified land. And then came the KPG boundary. The Chicxulub impact 66 million years ago deposited a distinctive ejecta layer across much of the planet. In the Hell Creek Badlands, you can stand at a specific thin band of clay and tektite spherules and see, directly, the boundary. Below it, Triceratops fossils, Tyrannosaurus teeth, mosasaur bones in the remaining brackish waters. Above it, nothing for a stretch, except a handful of fast-evolving Paleocene survivors. The non-avian dinosaurs, the last mosasaurs in residual water, the last ammonites in any basin that still had marine connection, all end at or within centimeters of this clay layer. The Western Interior Seaway, by this point, was almost entirely gone. What water remained, in scattered lakes, in coastal estuaries, in the Gulf itself, was no longer the grand seaway of the earlier Cretaceous. but the last creatures that had evolved within its ecosystem and that had moved into adjacent waters as the sea drained were in those remaining waters when the asteroid fell. They did not escape what was coming. Across a period of perhaps 10,000 years, perhaps less, the entire surviving marine reptile fauna of the late Cretaceous disappeared. The last mosasaurs, in whatever shallow basin they had retreated to, were overtaken by the impact winter, by the ocean acidification, by the collapse of the food chains they depended on. The last plesiosaurs went with them, and with the last ammonites, cephalopod survivors of 350 million years of oceans, were extinguished in the same interval. By the time the skies had cleared and the Paleocene had begun, none of the defining creatures of the Western Interior Seaway remained anywhere on Earth. What came after, in the early Paleocene, was a marine fauna of survivors, bony fish, early modern sharks, certain bivalves, certain gastropods, certain lineages of foraminifera. They would, across the next 66 million years, diversify into the modern oceans. Some of them would reach sizes and ecological roles comparable to those of the late Cretaceous. Some of them, particularly the cetaceans, whales, and dolphins, would occupy niches very similar to the ones the mosasaurs had held, but from a different ancestral lineage by a different route. The ocean repopulated itself, but the specific fauna of the Western Interior Seaway did not come back. The sea, by the time the Paleocene dawned, had drained entirely from the interior of the continent. North America, for the first time in 30 million years, was a single landmass. The seafloor of the Seaway, the Pierre Shale, the Niobrara chalk, the Mancos mudstones, the Fox Hills sandstones, was rising as the Laramide Mountains grew and the crust adjusted to become the elevated plains of what would one day be the American Midwest. The marine sediments were now physically continental interior, and they would stay there, exposed and eroded, for the next 66 million years until human hands and hammers and a modern eye came along to read them. What is left today is the rock. If you know where to go, and in many parts of the American Midwest, you do not even need to look very hard. The Western Interior Seaway is still unambiguously there. Its sediments are at the surface across vast areas of Kansas, Nebraska, South Dakota, Wyoming, Colorado, New Mexico, and up into Canada. The Niobrara Formation, the Pierre Shale, the Mancos Shale, the Fox Hills Sandstone, the Maury Shale. Each one represents a specific interval of the Seaway's existence, preserved in stone. In western Kansas, the Smoky Hill chalk member of the Niobrara Formation is exposed across hundreds of square kilometers. In parts of Gove County and Logan County, the bedrock is chalk so pure that it can be carved with a pocket knife. The famous Monument Rocks, a set of natural chalk spires standing up to 20 meters out of the Kansas prairie in the middle of what is now farmland, are Cretaceous chalk, eroded into strange freestanding pinnacles by the wind and the occasional rain of the high plains. They are, geologically, the remnants of the Seaway's floor. Each one walked up to is a column of coccolithophore corpses compressed into stone with ammonites and Inoceramids and occasional mosasaur bones embedded in them. The Castle Rock Badlands display the same formation in its full topographic strangeness: pillars, arches, ridges, all of them chalk, all of them nothing but the slow rain of the late Cretaceous plankton, preserved across 90 million years. The Sternberg Museum of Natural History in Hays, Kansas, holds the single finest collection of Western Interior Seaway fossils in the world. The fish within a fish, dozens of complete mosasaurs, Plesiosaurs with their long necks curled around their bodies, Pteranodons with preserved wing membranes, Archelons. A walk through its galleries is, in effect, a walk through the late Cretaceous food web. Every major guild of the Seaway has its representatives there. In Nebraska, Sweetwater County, and Wyoming, Large stretches of Colorado and other states similar material is found, though typically in less spectacular preservation. Fossil hunters, professional and amateur, still work the chalk beds regularly. New species of mosasaur are still being named even now. The Pierre Shale, a darker, organic-rich mud deposit laid down in the deeper water of the Seaway during its later ages, is particularly rich in ammonites and in the giant Inoceramids. Single outcrops can be tens of meters thick, with fossils at many different stratigraphic levels. In other places, the evidence is quieter. Oil wells in the Dakotas drill through seaway sediments every day. Farmers in Saskatchewan plow up ammonite fragments in their fields. The chalk that supports the underground aquifer of parts of the Great Plains is, at its origin, a late Cretaceous seafloor. The water coming out of the taps of some Midwest cities has passed through the compressed bodies of coccolithophores that lived before any mammal was bigger than a shrew. The Seaway is not gone. It is only emptied. Its floor is still here, in the rocks, under the surface of a continent that has since become one piece of land. It is unusual among the great deep-time ecosystems to be able to stand on top of one. The Permian oceans, the Cambrian reefs, the Ordovician shelves, all of them are scattered, fragmented, preserved in isolated outcrops on various continents. You can visit them, but you cannot, on any long drive, feel that you are crossing their territory. The Western Interior Seaway is different. It sits in the modern Midwest as a continuous presence beneath the topsoil, a sea whose bottom you are, geologically speaking, standing on every time you stop for gas along Interstate 70 in central Kansas. A few meters of loess and young soils and then chalk. A few more meters of chalk and then the Pierre Shale. A few hundred meters of Pierre Shale and then the older Niobrara again. And so on down, layer by layer, through the whole history of the Seaway, laid out in the rocks beneath your feet. The ocean that covered North America did not leave. It simply drained, and what it had done while it was there, the plankton it had nourished, the bones it had accumulated, the slow chemistry of its sea floor, it left in place, and then, across 66 million years since, waited, patient, unobserved, for enough time to go by that somebody would come along and read it. That reading is still ongoing. Every year, a few more mosasaur species are described. Every year, better reconstructions of the Seaway's ecology, its circulation, its seasonal dynamics are produced. Another farmer in Kansas finds an ammonite in a plowed field. Another fossil hunter extracts a new complete specimen from a chalk outcrop. Another paleontologist adds another small detail to the ecosystem's map. The sea is, in an unusually direct sense, still here. It is only that it is empty. It has been empty for a very long time. And if you stand in the middle of a modern Kansas wheat field on a warm afternoon with nothing around you for kilometers in every direction, you can, if you know the rocks and if you listen, still feel under your feet the quiet depth of what was there once. A subtropical sea. 1,000-kilometer-wide body of water, a water column full of creatures that no longer exist anywhere, a floor made of the bodies of creatures too small for you to see, a whole ecology in place for 30 million years. The world, which we often forget is old, still carries that history in its rocks. The middle of a continent is not a permanent thing. The shape you grew up imagining, the one solid landmass of North America, is, on the timescales that matter to the planet, a recent arrangement. Before it, and for a long time, there was an ocean here, and the ocean is, in every way except for its water, still here. That is the ocean that covered North America. That is the sea beneath your feet.